I'd like to welcome everybody to our webinar today. And it is my pleasure to introduce you to our speaker this morning, who is David Zierden, and he's the Florida State climatologist who's housed at Florida State within the Center for Ocean Atmospheric Prediction Studies, or COAPS. David also plays a critical role in the Southeast Climate Consortium and the Florida Climate Center. He's our local expert on El Nino Southern Oscillation and has also worked to develop a method for forecasting wildfire threat based on the Keach Drought Index, or KVDI, which some of you might be familiar with. So with that, I'll go ahead and turn it over to David to get started.
All right, thank you, Heather, for the introduction, and I just want to thank you and Ryan Boyles for inviting me to be a participant in this webinar series. I think you gave a pretty thorough introduction. I am here kind of representing the Southeast Climate Consortium, which is, as you know, a partnership of now 8 universities in the Southeast that had its beginning trying to make climate information and especially seasonal climate forecasting applicable to agriculture here in the Southeast. But we've grown and we've broadened our horizons, and we're now looking at climate variations of all time scales, including climate change, and we're looking at different sectors, including forestry, natural resource management, coastal, and water resources. So that's kind of who I am, and today I've been invited to talk about climate variability. And before we go into that, let me kind of clarify what we mean by that. When we talk about climate change, we're generally referring to a long-term continuous trend of changes in temperature or precipitation patterns, and it's recently the emphasis is linked on the anthropogenic increase in greenhouse gases. But when we talk about climate variability, we're talking more about natural variations that occur on many different time scales, from kind of month to month, or what we call intraseasonal, to year, which we call interannual, to 10 or more years at a time, which we call decadal or even multidecadal variability. So we're going to talk a little bit about all these, and all these variations on these different timescales have gone on in the past and will likely continue to occur in the future, and it gives us some predictability in the short term, but it also gives us challenges when looking at longer term in a changing climate. So with that, I'm going to begin, and I'm going to begin with really the key player in climate variability, and that's the El Nino La Nina cycle. Okay. I think most of you are probably familiar with the terms El Nino and La Nina, and have heard of this phenomenon in the Pacific Ocean and have a little bit of idea of what it means to our weather and climate patterns. But for review, let me talk a little bit about it. What I have here are 2 satellite images of the Pacific Ocean. On the bottom right is an image from November of 1997 during one of the biggest El Ninos of this century. Again, this is a satellite image, and the reds and whites actually represent sea surface heights, not temperature, that are greater than normal. But these images were made from a satellite called an altimeter that can measure the height of the sea surface very accurately within just a couple centimeters. But the sea surface heights are directly tied with sea surface temperature. So this red and white area represents a vast area of the Pacific Ocean that extends along the equator, basically from the coast of South America all the way to the international dateline, where sea surface temperatures are now several degrees Celsius, up to 4 or 5 degrees Celsius warmer than they normally are. Again, this was one of the largest El Ninos of the century, but I like this map projection because it shows that it's not just a little change in ocean currents on the other side of the world. The area of the Pacific Ocean that's affected is nearly the size of North America. And if we remember our geography, it's actually located just about due south of the southeast United States. So it's really not on the other side of the world. It's right here on our doorstep. And these changes in ocean temperature have enormous implications to our weather and climate patterns, especially in the winter months. Over on the top left is the opposite phase of the Pacific Ocean, or La Nina, where this roughly the same area along the equator can turn several degrees colder than normal, as represented by the purples and blues in this satellite image. These El Nino and La Nina events, they tend to return every 2 to 7 years. Looking over the long-term history, we're in a El Nino about 1 out of every 4 years. We're in a La Nina about 1 out of every 4 years. And then the other 2 out of 4 years were what we call neutral, or when the sea surface temperatures are much closer to normal. But this El Nino-La Nina cycle is the predominant driver of climate variability here in the southeast United States. That's not the truth. It does have implications for other parts of the world, South America, of course, Australia, Indonesia, other parts of the globe. But some parts of the globe really don't feel this climate impact as much. But we're lucky or unlucky, however you want to look at it, here in the southeast. We feel it very strongly, and it really is a major driver of our year-to-year climate variability. In fact, here's a quote I loved from Bob Livesey, who was the former head of the National Weather Service Climate Services Division. He says that the El Nino, in the absence of an El Nino or La Nina event, that the seasonal forecast from the Climate Prediction Center lack useful skill. So this El Nino-La Nina cycle is really kind of the golden nugget now that gives us some predictability of our climate patterns from 1 to 6 months or even a little longer out. So let's take a closer look at what this phenomenon in the Pacific Ocean is. Here's a graphic of the usual state of the Pacific Ocean, the winds and ocean currents. This area along the equator here in the tropics is dominated by what we call easterly trade winds. These are just very persistent surface winds. They blow all throughout the tropics, generally from east to west, and they're a very consistent, very ever-present feature. These trade winds blowing all the time. And because of these easterly trade winds, we get cold water upwelling off South America here. Because of these winds, we have upwelling. It brings up cooler, nutrient-rich waters, and they tend to be trapped and flow along the equator. Where over in the western Pacific, this is what we call the warm pool, where some of the warmest ocean temperatures of the world reside. And these ocean temperatures, 82, 84 degrees Fahrenheit, are warm enough to support a lot of cloudiness and rain, thunderstorm activity, which is called convection. Now, during an El Nino, what happens is these easterly trade winds can be disrupted or relax, and sometimes they can even switch where we get a period of west winds. And this sets off a chain reaction of internal waves in the ocean, which propagates eastward, and during the height of an El Nino, will even shut off the upwelling off South America. And once the ocean temperatures start to warm up over in the eastern Pacific, it kind of reinforces the change in these trade winds, and it's a chain reaction cycle that builds on itself until you have a full-blown El Nino. For a La Nina, much the opposite occurs. The trade winds get stronger than normal, and you get enhanced upwelling that kind of builds on itself and builds into a cold event or a La Nina. What I have here is schematics of the ocean and the atmosphere during the El Nino events and La Nina events. Up here on the top left is the ocean temperatures during El Nino, where now you see this warm pool that's usually confined to western Pacific has now spread across nearly the entire basin. And with that warmer water comes the increased cloudiness and rain and convection, which is a very efficient mechanism for transferring heat and moisture from the surface into the upper atmosphere. When we have a La Nina, on the other hand, as shown on the bottom right, you get the enhanced upwelling, the colder waters extending well west of the international dateline, and now the warm pool is pushed further west, confined to Indonesia and Australia, much less convection and transfer of heat and moisture into the atmosphere. So this sets off a pattern of atmospheric circulation unique for the La Nina events. So what are some of the implications of the El Nino and La Nina? Well, of course it has a major impact on the coast of South America, Peru, Ecuador. One story is of the anchovy fishery off the coast of Peru. There used to be a tremendous resource for anchovies, averaging 30 million tons or so harvested yearly. During times of El Nino, you get the upwelling shuts off, the warm water moves into the coastal areas, and the anchovies disappear. And actually in 1973, I believe it was, there was a strong El Nino that really shut down the anchovy fishery, and that combined with overfishing, it never really recovered. And they went from harvesting 30 million tons a year down to 2 million tons. So big implications for the coast of South America and Peru. They also get torrential rains during El Nino. The picture on the right shows flooding and tremendous erosion from the rains that El Nino brings. Interesting enough, this El Nino La Nina cycle has been going on for centuries. It can be traced back in the journals of Spanish missionaries in the area, that they would remark when they'd have a particularly rainy year, and it would coincide with the El Ninos. So we know it's been going on for hundreds of years that way. You can also look at coral rings from Pacific islands that they have annual growth rings similar to trees, and the size of these growth rings are affected by the ocean temperatures and productivity. And you can trace the El Nino La Nina cycle back thousands of years in these coral rings. So it's nothing new, even though we've only heard of it in the last 20 or 30 years. Well, how do we know what's going on in the Pacific Ocean? We had one of the largest El Ninos of the century in 1982 and 83, and this was a very large and strong event. It came on suddenly, and while residents of South America and oceanographers were well aware of this phenomenon, the weather and climate community really didn't pay much attention to it. Well, the 82-83 event caused worldwide disruptions. Winter storms and coastal erosion in California, torrential rains here in the southeast, terrible drought and wildfires in Australia and Indonesia. Worldwide, the impacts of that El Nino were billions and billions of dollars. So it really opened the eyes of the scientific community to how the Pacific Ocean can affect our weather and climate patterns. And then through an international cooperation, a whole series of buoys were deployed in the Pacific Ocean. Here on this map on the bottom left, you see an array of blue dots. Everywhere one of these blue dots are is a weather buoy, as shown on the right. And these weather buoys measure atmospheric variables, winds, temperature, barometric pressure among them, but they also measure oceanic variables like sea surface temperature and currents, and not just at the surface, but down several hundred meters. So these buoys are a huge undertaking, but they are in place now. They telemeter their data back real time, and so now we'll never be caught unaware again as we were in 1982 and 83. We monitor the Pacific Ocean daily, and with this data we can actually model this El Nino and La Nina cycle and have better predictions for it. So let's take. I talked a little bit about the history of El Nino, but let's take a closer look at that. The way it's most commonly done is with what we call a Nino Index. What I've shown here is the Nino 3.4 index, which is nothing more than the sea surface temperatures in this little box here in the eastern and central Pacific Ocean. You take the sea surface temperatures from this area, compute their departures from normal or anomalies, and plot it month by month. And we've done that over here on the left. This plot goes from 1950 on the top left all the way to the present time on the bottom right. And to explain this graph real quickly, these lines are at plus or minus half a degree Celsius. If the variation is within those two lines, it's close to normal, and we call that neutral. Where these red spikes, these are when it's warmer than normal, or the El Ninos, and you can see them. Here's the first great El Nino of 1982-83. I'm sorry, here's the 82-83 event. No, I'm having trouble reading my own graph. No, this is the 97-98 El Nino, which in some measures was bigger than the 82-83 event. But anyway, the orange spikes are the El Ninos, where the blue valleys are the La Ninas, when it's colder than normal. And some things to take away from this graph: it's not entirely regular. It doesn't swing from El Nino straight to La Nina, then back again. They kind of come a little bit randomly, like I say, every 2 to 7 years, and there can be long periods when really nothing's going on. Another thing to take from this graph: the El Ninos tend to be one-year events, where the La Ninas, on the other hand, can often last 2 or 3 years, like they did in 1954 through 56, 74 through 76, more recently in 1998 or 99 through 2000. So this is important because, as I'll show you in a minute, La Nina tends to bring warmer and drier weather to the southeast, especially in the winter and spring months. And these multi-year La Ninas, and especially, are the trigger for some of our longest and most severe droughts here in the southeast. Real quick, uh-oh, I need some help. I just lost my slideshow. Okay, I'm sorry. It's still kind of new on Illuminate. Anyway, let's take a look at more recently what's happened in the Pacific Ocean. We are in the second year of another multi-year La Nina. Here on the left shows the current sea surface temperatures themselves and the departures from normal on the bottom. And looking at this top graph of the sea surface temperatures, you see the cold water extending up from South America, represented by the blue colors, and extending along the equator, even over to the international date line. And then you see the warm pool here is fairly small and contracted and confined to the far western Pacific. Looking at the departures from normal, again, the colder than normal is shaded in blue, and you see a broad area of the Pacific Ocean, 1 to 2, even 3 degrees Celsius colder than normal. And this is really a classic pattern of a well-developed La Nina. So that's what's going on currently in the Pacific Ocean. If you look at the graph up here, especially the second from the top, this is that Nino 3.4 index that I showed on the previous graph. This is just from the past year. And you can see starting in January of 2011, we were in a very strong La Nina. The ocean temperatures returned to normal in the spring, and actually were very close to normal in the summer months. But as was predicted by Klaus Walter and others, this La Nina did re-intensify this fall and is back again for a second year. So what does that, now let's get into the good part. What does that mean to the climate and weather patterns of the southeast? Well, these are schematics of that kind of represent the circulation patterns of our atmosphere here in the northern hemisphere, especially in the winter and the cold weather months. These are the predominant jet stream patterns for El Nino on the left and for La Nina on the right. And when you have an El Nino in place with all this extra heat and moisture down here in the tropics, it tends to set up a pattern with a very strong subtropical jet stream that flows zonally or west to east across the Pacific and the southern tier of the United States. And this is kind of a storm track. Storms will develop in the Pacific Ocean, these winter storms. They'll impact central and southern California. And then these low-pressure systems will frequently redevelop along the northern Gulf Coast and tap the abundant Gulf moisture and track right across the northern Gulf Coast and the state of Florida up the southeast Atlantic coast. So that's kind of the predominant storm track during El Ninos. Brings us much wetter than normal weather patterns here in the southeast. Just from personal experience, in a normal winter, we'll get a frontal passage or a rain event about every 6 or 7 days. During an El Nino, that seems to jump up to every 2 or 3 days almost. We'll be getting a new weather system and another round of rain. So it's frequent storminess when we get this pattern set up. Now over on the right shows the typical jet stream patterns during La Nina. And this characterized the subtropical jet now without all this heat and moisture from the tropics is much weaker or often not even a player in our weather. It's the polar jet is the more dominant jet stream during La Nina, and it tends to set up a pattern of high pressure ridging over the eastern Pacific Ocean and the western U.S. and kind of a mean trough along the central U.S. But the storm track from this configuration, the winter storms and low-pressure systems tend to track along the mid-tier of the United States, kind of up the Mississippi Valley and through the Northeast. You actually get some wetter than normal patterns here along the Mississippi and Ohio Valley due to that storm track. But here in the Southeast, especially the Peninsula of Florida, we're often at the tail end of things and not under the favorable dynamics, and we get kind of more dry fronts. The cold fronts don't pack as much punch, so we get more sunny days, more warm weather, and a lot less rainfall. So now let's take a closer look at what these changing jet stream patterns really do to our precipitation patterns in the fall, winter, and spring here in the Southeast. Well, what I'm showing here are known as El Nino or La Nina composites, where we've taken over 100 years of historic climate data and just broken it down into the 3 phases of the Pacific Ocean, when you have an El Nino going on, when you have a La Nina going on, or when it's neutral. And by just differencing and by grouping all the El Ninos together and subtracting them from the neutral average, the impacts on our precipitation really jump out. So that's what we've done. Up here on the top left shows the typical changes in rainfall when we have an El Nino in place by just grouping all the past El Ninos together. And what you see enhanced. This is for the month of January, which represents winter patterns. And you see enhanced rainfall by the purples, blues, and reds of 10 to 20% in the greens and up to 40 to 60% in the purples. And this shows enhanced rainfall over the peninsula of Florida, 40 to 60% more rainfall than normal in the winter due to El Nino. The pattern tends to lessen as we get up into Georgia, South and Central Georgia, and the Carolinas, but there's still a significant change in rainfall of 20 to 30%. So this is for the month of January, but it represents pretty much the pattern from November through March. As we get into the summer of the year, when an El Nino is in place, well, the first thing, the impact of the Pacific Ocean on our climate patterns is not nearly as strong in the warm weather months because the jet streams have migrated north and there's really not as much of a connection. But still, in the summertime, when an El Nino is in place or is forming, we tend to get a drier late summer, as shown in this graphic on the bottom, where we sometimes see rainfall departures of 10 to 20% less rainfall than normal in the summer when an El Nino is building. Doing the same kind of technique, we can see the impacts of La Nina, or cold water in the Pacific Ocean, on our rainfall patterns. And top left shows the changes for November, which we certainly saw this year. The whole southeast is now drier than normal, 10 to 20% less rainfall than normal across the whole southeast, even 20 to 30% over South Georgia. And as we get into the wintertime, this pattern actually intensifies and moves south. Now the peninsula of Florida is 40 to 60% less rainfall than normal, and that extends along the Atlantic and Gulf coastal regions. There is a transition zone during La Nina, and we see it very clearly this year between where you get actually enhanced rainfall up the Mississippi Valley, in northern Alabama, and even in northwest Georgia. We also instead of taking a broad regional view, we also like to take a look at the local impacts of El Nino and La Nina. This just shows for Hillsborough County, Tampa, Florida, again, the changes in rainfall for El Nino on the top left. You see the enhanced rainfall throughout the winter months and the dryness that can set in the summertime. La Nina, you see the decreased rainfall basically from November and December all the way through March and April. But just looking at the changes in average is not always sufficient. What we've done here is taken the same historic rainfall data and worked up a probability of exceedance curves for two of the phases of the Pacific Ocean. And the way to read these graphics is this is the probability of getting 2 inches or 3 inches of rainfall or more. And again, this is for Tampa, Florida in the month of March. What I've shown here is normal March rainfall is about 3.7 inches. And during El Nino, the likelihood of getting normal rainfall or more is very high, over 70%. Whereas if we look at La Nina, here on the bottom right, now I've got normal rainfall marked here. Now the probability of normal rainfall is only about 16 or 17%. So it's over 3 times as likely to get normal rainfall or above in El Nino than it is in La Nina. But you also have to look at all these kind of climate forecasts in a probabilistic sense, because even though it's unlikely, we can still get heavier amounts during the La Nina. It has happened before. It'll probably happen again. So while it's still possible, the change in probabilities are very significant. This El Nino La Nina cycle also affects our temperature. Real quickly, this just shows, demonstrates winter temperature departures from normal during the La Nina phase, and you see the whole southeast is warmer than normal. The brown shaded areas 2 to 4 degrees warmer than normal. So it lines up very good with what's going on this winter, where we've had these really exceptionally warm temperatures all winter long. It's not always the case, as I'll go into in a slide or two. Some other impacts from El Nino and La Nina. It has a major impact on the activity of the Atlantic hurricane season. Here I show storm tracks over the last century of major hurricanes, Category 3 or above, that have hit the United States. And these are the historic storm tracks for major hurricanes during the El Nino phase, or when El Nino is in its formative stages in the Pacific Ocean, and for the La Nina phase over here on the right. And you see nearly 2 or 3 times as many major landfalling hurricanes in the La Nina phase as El Nino. So knowing this, we like to do statistics on these kind of things. We looked at over a century of landfalling hurricanes in the U.S. and worked up the same kind of exceedance curve. Again, the way to look at this is the likelihood of one or more hurricane, and this is all hurricanes now, Category 1 and up. The likelihood of one or more hitting the United States in any year is high. The red line is El Nino, the blue line is La Nina, the green is neutral. And for all three phases, it's high that will be impacted by at least one hurricane, over 70%. As we get out to two hurricanes or more, the likelihood during El Ninos falls to nearly 30%, where during La Nina, it's up 65%. So it's twice as likely that we'll be hit by two hurricanes or more during the La Nina phase than during El Nino. Go further out, only once have we had three hurricanes impact the United States during El Nino. Yet during La Nina, it's fairly likely, nearly 40%. So it's a huge shift in odds. And actually another study we did where we looked regionally, this increase in landfalling hurricanes during La Nina is felt most strongly along the U.S. East Coast, not so much in Florida or the Gulf Coast. So the take-home message from there is when we have a La Nina phase in place, the Carolinas and the East Coast are at greater risk for a hurricane landfall. Some other impacts that'll interest this group is on the Florida wildfire season. Florida's kind of unique because the peninsula of Florida has a dry season in the wintertime that extends basically from October through April. And during La Nina, when you get an even drier dry season, we're really at risk for greater wildfire activity. And this satellite image shows one of Florida's largest fires in 2001 during the La Nina event. Here, this graph just shows our typical wildfire season in Florida, beginning in January and through the winter months, so it's fairly active. And then as we get into the spring dry season and when evapotranspiration increases, we really get peak activity around late April, May, and even into June in some years. But once the summer rainy season starts and we start getting the daily afternoon thunder showers, wildfire activity drops off to nearly nothing, and the wildfire season is effectively over. But like I was telling you, this El Nino La Nina cycle does have a huge impact on our wildfire season. Here in the line, I've plotted the Nino 3.4 index that shows the El Ninos and the La Ninas, and I've also plotted anomalous wildfire activity in acres burned in blue for the early wildfire season and in green for the late spring, early summer period. And you see during La Nina, we tend to have less wildfires. During El Nino, less wildfires due to the plentiful winter rains, where during La Nina, we get enhanced wildfire activity. And it's a fairly strong correlation here, and the Florida Division of Forestry really uses this prediction and pays attention to the phase of the Pacific Ocean for planning their prevention measures. We've even gone a step further, and based on the phase of the Pacific Ocean and historic climate data, we've developed a method for actually forecasting the Keach-Byram Drought Index. This is our forecast for this year. What this forecast shows is the probability of different thresholds of the Keach-Byram Drought Index. Here we chose 550 because that's pretty much an actionable level here, where outdoor burning is banned and countywide bans are put in place. So this shows the forecast for February. What is the likelihood of reaching 550 for at least 7 days in the month of February? You see a very high likelihood in the drought-plagued areas of west central and southwest Florida. Up here in the Panhandle and Alabama, we've been getting some winter rainfall, so the likelihood is very, very low. So we've developed this product. It's available on AgroClimate. All right. I really wanted to stress the El Nino La Nina oscillation because it's king here in the southeast and really gives us some predictability that we wouldn't otherwise have. But it's not the only player in town. There's several others, or lots of other natural variations or climate oscillations, and operating on different time scales, and I'd like to touch on some of those now. We'll begin in the intraseasonal or month to month, something that affects our weather patterns. And the first is the North Atlantic oscillation, or NAO. The NAO is basically a difference in surface pressure between Iceland and the Azore Islands. And this NAO has a positive and a negative phase. And the positive phase, first let me give a little climate background. Our winter patterns there's some semi-persistent features over the Atlantic Ocean. There's the Greenland Icelandic low, which is a fairly persistent area of low pressure here in the northern Atlantic. And then there's the subtropical or Bermuda high down in the tropical Atlantic. And so during positive NAO, this low pressure is stronger than normal, the high pressure is stronger than normal, and it sets up one kind of jet stream pattern. The one that we really have to watch out for is when this NAO is negative, when we actually have weaker low pressure, weaker high pressure, which allows this storm track to drift a little more southerly. And so the negative NAO leads to troughing or lower pressure in the eastern United States and kind of an avenue for Arctic and cold air to enter the eastern U.S., snowstorms to develop. And I'll show you a little bit more about it on the next slide. This shows kind of surface pressure departures from normal during the negative phase of the NAO, and you see the very strong colder temperatures over inland Canada and the polar continental area, and this negative NAO really allows this Arctic air to flow down in and affect the eastern United States. And this graphic shows the long-term and NAO and from last year, and again starting at 1950 going through the present. What's interesting is the previous two winters, the 2010-2011 winter and the 2009-2010 winter. The 2009-2010 we were in El Nino, 2010-11 we were in La Nina, but during both of these phases we were in a very persistent and highly negative NAO, which was responsible for the frigid temperatures we experienced each of those winters. Not this past December, but December a year ago was one of the coldest ever in the southeast, and that was during La Nina when we expected warmer temperatures. The same thing during the 2009-2010 winter. We had one of the coldest Januaries ever. Here in Tallahassee, we had 14 days in a row of freezing or below. And so this NAO was really playing havoc with our climate patterns. Over on the right, however, this graphic, this index has been highly smoothed or averaged out over time. Over on the right shows more of the day-to-day fluctuations in the NAO, and this is from last December. And you see it kind of comes and goes in a matter of days. And this makes it very problematic for using it as a predictor. And in fact, the NAO, in my opinion, is more of just an indicator of the large-scale circulation pattern than it is a cause and effect. So it can change drastically over the course of just a few days and really doesn't have a lot of predictability out past 2 weeks or so. So while we can look back and say, yeah, last winter was dominated by a negative NAO, it's really difficult to predict going forward. I'd also like to mention the Arctic oscillation, which is kind of very closely correlated with the NAO. In fact, the North Atlantic Oscillation is just kind of one aspect of this Arctic Oscillation. And without going into a lot of detail, during the negative phase of the Arctic Oscillation, you have higher pressure, or actually what more correctly is weaker low pressure over the polar regions. This polar vortex is a little slower or a little less energetic than normal, and it allows a more southerly and more variable storm track. And this negative phase of the Arctic Oscillation is right in tune with the negative phase of the NAO, or North Atlantic Oscillation. In the positive phase, this polar vortex is stronger, a more well-defined and more northerly storm track, which means more mild winters for the eastern United States. Another oscillation that's out there is in the Pacific Ocean. It's called the Pacific Decadal Oscillation. It's characterized by changes in ocean temperatures in the northern Pacific. During the negative phase, the western North Pacific off Japan is warmer than normal. Here along the western coast of the United States, it's colder than normal. During the other phase, or the warm phase, we get warmer water off the western United States, off Mexico and Alaska, and colder waters off Japan. So if we plot this index monthly for the last century or more, there you can see it's quite a noisy index, but also there are prolonged periods of warm PDO and cold PDO, and there was a very pronounced shift both in about 1948 or 49 and again in 1976. Now this Pacific Decadal Oscillation has some pretty significant impacts especially on temperature in the western United States. Here in the southeast United States, it works more hand in hand with the El Nino La Nina cycle and kind of modifies the impacts of the El Ninos and La Ninas, but certainly doesn't override them. One last oscillation I'd like to look at is called the Atlantic multidecadal oscillation. And what this is a change in sea surface temperatures of the whole North Atlantic Ocean. And the magnitude of these changes is not very great. Here on this graph you see it's from 0.2 of a degree Celsius to negative 0.2 of a degree Celsius. But there have been distinct multidecadal periods of cold and warm AMO. And this AMO is pretty well known to be tied to the activity of the Atlantic hurricane season. You get more hurricanes during warm AMO, as we did in the 40s through the 60s, and then less active periods when it's cold, as we did in the 70s and 80s. Here, this one study actually ties rainfall patterns in south central Florida to the Atlantic multidecadal oscillation, but this is more of a local phenomenon. This correlation between rainfall and the AMO really doesn't extend up into North Florida or into the Carolinas or other parts of the Southeast. So while it's a little bit of a predictor, it's really not a strong correlation. So with that, I wanted to just touch on some of the better-known oscillations, and to summarize, the El Nino La Nina cycle is still king because, one, it's very well understood the physical connection between the Pacific Ocean and our circulation and climate patterns. It's been very well studied, and the physical connection is well known and can even be modeled. These other oscillations are a little more tenuous. Like I say, the North Atlantic and Arctic oscillation are more just an indicator of the pattern rather than a cause and effect. And then the correlations of these longer-term oscillations, like the AMO and PDO, are not nearly as strong as with the El Nino La Nina cycle, and not nearly as identifiable or predictable. Kind of the holy grail for climate prediction is if we were to find how all these oscillations work together and be able to combine them all in a way to give us a more useful and accurate forecast. But a lot of work has to be done both to understand how they work together and how to make a forecast using all of these. So there's still lots of work to be done in the climate variability and forecasting arena. In closing, I'd like to take a look at some of the longer-term changes we've seen here in the Southeast and that may or may not be tied to any of these climate oscillations. The first, I'd like to take a look at impact freezes on the Florida citrus industry, and it really tells an interesting story. In John Attaway's book, A History of Florida Citrus Freezes, he lists over a dozen freezes that had a dramatic impact on the citrus industry, beginning in 1835 and going through 1997. And in his book, he comments that prior to 1835, they actually called it the warm century, where viable citrus orchards were grown in colonial areas such as Savannah, even as far north as Charleston. But then this freeze in 1835 devastated those more northern orchards. Then we had another cluster of freezes in 1894 and 1895 through the beginning of the century. Citrus industry had begun thriving here in North Florida around Jacksonville and Palatka and the St. Johns River. This cluster of freezes really devastated the industry there. As we got further into the 20th century, the center of the citrus industry was more around Ocala and the Orlando area, Disney World, where we remember it. But then we got into another cluster of freezes in 1977 through 1989. And due to this whole series of catastrophic freezes and to just pressure from development, the citrus industry has moved even further south now to where it's down near the western shores of Lake Okeechobee and places like Immokalee, Okeechobee County, places like that is now where the heart of the industry is. So here we have certainly multidecadal variations in extreme temperatures and the climate change and an industry adapting to it. Here's another interesting story is if we take a look at average annual temperatures here in the Southeast, I've chosen Alabama as kind of the poster child for this. We see a very strong multidecadal variability in temperatures. Here you see in basically the 1920s through the 1950s, some of the warmest years on record in Alabama, and consistently warmer than normal. Then we seem to have a regime change in about 1958, and we went into a series of cold decades. Here in 1958 through 1980, every year was colder than normal. And then as we get into the more recent decades, we've returned more to normal. But there's really a very strong multidecadal change in temperature. And it wasn't just in Alabama. If we define the warm and cold period as these years that I've shown here and simply difference the two, you see there's significant differences in winter temperatures between these two periods throughout the Southeast, up to 4 degrees Fahrenheit or more. And this is in the difference in overnight minimum temperatures. We also see the same difference, but not as strong, in the afternoon maximum temperatures. We also see these differences in temperatures in all seasons of the year, including summer, but they're not as strong as the winter differences. And it's not just average temperature that change during these different regimes. If we look at the occurrences of extremes at a couple different stations, here in Lake City, this is the number of freezing days that could be expected during a year. And during the warm period, there were only half as many freezing days as during the cold period. Likewise, if we look at extreme heat, days over 95 degrees in an Alabama station, again, you see twice as many during the warm period as during the cold period. So there were this distinct multidecadal pattern of variability in temperature, but it's not necessarily tied to any of the oscillations I showed you. These breakpoints that I showed you don't match up with breakpoints in the Pacific Decadal Oscillation or the AMO. So something else is going on that caused this multidecadal change in temperature that we don't fully understand yet. So I think I'm sorry I went too long. I hope there's still time for a discussion, but that's just kind of a look at climate variability here in the Southeast and some of the drivers of our climate variability.